Hi, everybody. Welcome to Ellensburg, Washington, USA, on the campus of Central Washington University. Thank you for joining us today. The local time is 11:49, and we'll begin our lecture, our guest lecture, in about 11 minutes from now at the top of the hour. So if you're watching this in replay, and that's most of you, feel free to skip ahead 11 minutes, and you'll get to the beginning of the program. Can I see if we're doing okay? Are we 5 by 5? Can I say hi to a few of you? And I've got a couple slight modifications to what we normally do here. We're experimenting as we go. So Don and Doug and Eric and Paul and Stevie Pinhead, Backcountry Gary, and Carla, they all say 5 by 5. So thank you. That's nice. Comforting. Where are you viewing from? Can I look at a few of your locations, please? And then we'll just see how things are going here. Laura's in Lake Chelan, Yorkshire, UK, Forest Grove, Oregon, Grimsby, UK. Hello. Bab, is that Bab, Montana? The Bab Bar. I have an interesting memory from the Bab Bar. If you're in the plains of Montana near Glacier Park. Nassau, New Hampshire. Hi, Jennifer and Boise. Haven't seen you in a while. Scrolling too fast now. Odense, Denmark. Plain, Washington. That's Rachel. Hello, Rachel. Oh, good Lord. Oegstgeekst, Netherlands. Hello, Hans. Sorry about the pronunciation there. New Jersey, Oregon, Minnesota, Selah, Washington, Paw Paw, Michigan. That's Hannah Shamlou behind me and our guest, Will. And that's our little wrinkle today. We're not turning on the guest's microphone until we're about ready to go, so that he can visit with whomever. We're doing okay?
Yeah.
Okay, great. So Vindman's Bakery is here yet again. Jeff has been providing these baked goods for free. This is, we even did this a few Fridays when we didn't have a talk. So we're into half a dozen of these trips, and the generosity is incredible. I don't know how long it's going to last, to be honest with you. I want to make sure that I'm not taking advantage of Jeff's generosity, so I'm continuing to visit with him about that. But he'll be here again today. He's getting a chance to visit with all of us, and so you should know, if you don't, about Vindman's Bakery in beautiful downtown Ellensburg. And I say downtown as kind of a joke. It's like right across the street from campus, basically. So that's where we are with that. A few more hellos to where you're viewing, and Walter's in wardrobe right now. Walter's going to say a few things. I think we'll wait until we do it with the crowd. I think we'll do much simultaneously. But thanks for being up here. Hey, there's Michael in Trim, Ireland, who made the journey to the Channel Scablands this summer. It was nice to visit with you, Michael, and family. Carla, Dennis is in Ottawa, Canada. Brian is trying like hell to get to Ellensburg to visit Vindman's, and Discovery Hall hasn't worked yet. Yeah, I don't know. I mean, the weather's getting crummy, but we got a bunch of empty chairs here. I think if you really want to come to the next one of these, you should come. That's November 18th. If you want to come, Friday, November 18th. That, just between you and me, I think it's okay if a few of you show up. Chris, you okay with that? I'm going to get myself in trouble. I think come on. How many empty seats have we had on average in here? Would you say at least 20? 20 of you. Why don't you get together and come up with a sign-up sheet and send 20 of you. Tanya, hello. Wausau, Wisconsin. A few more locations, please. It's always fun. I'm getting cocky now. I'm not even that worried about the technology today, which is a classic mistake. But Dave's in Ohio. IC is on Martha's Vineyard. Say hi to Carly Simon and James Taylor for me, please. Greater Good. Show us the Vindman's product. Yeah, it's outside. Spokane, Washington. Gene's in Puyallup. Gene, you've been a generous person over the last couple of years. Thank you for that, Gene. Oscar says hello from the Mexican border. Is that a creative way of saying San Diego? Oscar? Montana, Peshastin, Ottawa, Canada, Ritzville. Okay, well, let me swing the camera around for just a couple of minutes, give you a sense of who's in the room. Thank you. Thank you for being with us, and our lecture will begin in about 6 minutes. Aren't you happy to be in a nice, warm, dry room right now instead of shivering out there?
I was plenty warm all week. Everyone else was cold. I just added a layer every day.
That's a veteran move, Walter. You know how to dress for the weather. Oh, front and center, Jordan Carey. Oh, look at that. Yeah.
What's the Norwegian saying? There's no bad weather. There's just poor clothing choices.
Know what they say? Smug Norwegians. Pretty good crowd. I thought we'd be kind of dead today. Popcorn, hey. There's a serpentine family of chords, so maybe I'll have you come all the way around or whatever. I don't know. It's yeah. We're going to test your audio, young man.
Okay.
You keep chatting, you guys. Just be aware. Yeah, that's all right.
Yeah. Wow.
Hello, YouTube.
I just like blew out someone's speakers in like the Netherlands.
Testing the audio of Will. Can you hear Will right now?
Testing. Can everybody hear
Could I
me?
see Will 5x5, please?
And I sit up there because I have to take attendance, but I monitor the chat and it's very popular.
Could you write the word Will and then 5x5 just to make sure that you
Shout
can
out
hear
to
him
the
as
Issaquah
well?
Alps Trail Club.
You should say that. What would you think?
Thank you, Chris. Thank you, Brian. Thank you, Doug. Okay. Will is quite loud. Will, you're quite loud.
Okay.
We thought we were blowing people out.
Yeah.
We'll take it down a notch.
I do. I have been told I have a loud voice.
That's a
And
good thing.
I was a theater kid in high school, so I also project.
Okay,
So I'm like,
The sun will come out.
I default to like speaking to the audience like I don't have a mic on, so I'll
This is
try
perfect.
to
This is
I'll try to
perfect.
tone it down maybe a little bit though. I don't want to ruin anybody's
No,
ears.
we want you to project to us.
So do you guys
Is
not
Will
hear what's in
still
the mic?
way too loud, or is it
The
okay?
mic just goes to
Yeah,
YouTube.
that's
Okay.
Will, there's 6x6.
But like, still, please feel free to talk.
Okay.
To us.
Yeah, Nicole had the crappy microphone last time. Remember her mic cut out, so I've got the crappy one. I gave the good
It's
one
cool
to
little.
I know. It's a
Will. I'm just a hero that way. Will's okay? Okay.
Yeah.
Be nice, I guess, if I had some headphones so I could hear. There's always something.
It's like the
That
same
occurs to
feeling
me.
I would get before cross country races in high school.
Okay, we're good, huh? Both of us? All right.
Yeah.
We're going to start in 2 minutes. Thanks for joining us.
Can I restart?
You're not on
I was
camera
like-
yet, but I think Ann will stand right next to me, and then I'm going to have Walter talk a little bit
Because I
about the
want to be able
trench
to
as
know.
well.
Yeah, I
what
did
I'm
the same
taking.
thing. Did you restart it?
No, I didn't.
Oh,
But I don't
but
want to
you will
restart
use
it
it.
now. Wait till I'm
This is
actually
Narcissism
starting.
101.
You
Walter.
control.
Yeah. This is overkill. Okay, I grant you there. Okay,
Yeah, they have a handheld one.
Yeah, I'm pretty sure it works.
right.
Nick used it earlier and it worked. And if not, I'll just use the.
Apple glasses when they
I
come out.
have a bunch of extra slides at the end too. I have like 20 extra slides.
Oh,
Because some of the stuff I'm just like, I did a thing and I
All
don't
right.
don't like get too much into it. And so I was like, I'll put all the like really technical stuff in extra slides.
that's so good.
So
Is that an 80s reference? 90s reference? What?
Oh, drama is definitely the
I didn't do any musicals. I was a Shakespeare kid. So I was
YouTube listening.
I know. YouTube's learning so much about me. What I was the one of the like workshop people in Midsummer Night's Dream, the one who's like playing the woman in the play. That was like my
That sounds
best
like a
role, I
blast.
think. But yeah, yeah. I mean, you did dance. That's like it's there.
It's art.
Okay, everybody, I think we will begin today. Thank you so much for being on time. So gloomy out there, and I'm glad that you made time to come in here and join us today. We've got a good thing going. If you have not yet visited with Bree McGinnis about paperwork involving these live streams, please do so on your way out. That would be wonderful. I've got a quick announcement about the next few Talk Fridays, and then Ann Egger's going to say a couple things, and then Walter's going to say a couple things. Okay, so we're rolling with these noon seminars. Next Friday is Veterans Day. No school, so no Talk Friday. 2 weeks from today, Ice Age floods. If Joel Gombiner can get over the pass on November 18th, we'll manage to make it over with rain, but we'll keep our fingers crossed that Joel can get over in 2 weeks. And he's got some brand new ideas and new research. Just defended his PhD on the Mansfield channels in Moses Coulee and potential water coming down Moses Coulee, for those that know that area. So that'll be an interesting talk, very different from the topics we've been doing so far this fall. Then another week off for Thanksgiving, and then our final Talk Friday this fall will be the last day of regular classes, December 2nd. Megan Miller, who's a retired geology professor, she hired me 30 years ago. She lives back in town now, so she's going to talk about her career and her path from beginning to end. So that's coming up for 2 more Fridays after this. But we've got a good thing going. Thanks again to Jeff from Vinman's Bakery. Another round, please. Department chair, co-chair Ann Egger's got a couple words, and she's going to stand right next to me because she doesn't have a microphone.
Is this close enough?
Yep, you
Okay.
bet.
Just a reminder, I sent out an email this morning, but if you are an undergrad geology major and a transfer student, which I know is a lot of you, please join us on Monday, 2 p.m. in the 101 lab, room 110. We'll have some pizza. We want to hear more about your experience and help make that path smoother for other students in the future. I'm sorry, I won't be able to help you smooth your path in the past. I know that there are a few of you that have labs starting at 2. If you are one of those people, please come at 1:30 and we will still have pizza for you. Thank you.
Thank you, Ann. It's my bad. I'm not sure you were totally on camera, but these guys got you. So, Walter, I'm stepping forward to make sure you're in the shot. So Walter has been busy this week in the field with his master's student. I thought it'd be fun to hear what's been going on with you guys.
Oh, I didn't do much of the work. It was all my grad student Garrett. Garrett has gotten everything ready, and we've excavated 2 paleoseismic trenches in the Kittitas Valley. Hopefully, along the same fault, we'll find out all the story as we continue. Hopefully, the weather will clear and we can do some more of the mapping of the trench walls and figure out the story of the most recent earthquake in the Kittitas Valley.
So trenching means you actually got a backhoe?
Oh yeah. Yeah, it was a very large backhoe and very skilled operators, and they dug an amazing long trench, 26 meters long for one of them. The other one must have been something like 40 meters long and about 8 feet deep.
Up by the Ellensburg airport?
A couple places. They're on the north side of the valley, so they're up off of Nanum Road and then up off of Reeser Creek Road.
So you thought you'd be gone today and you guys would be out there, but you got rained out.
It's actually snowed out.
Snowed
so
out.
It's rained out here. There was about, according to Logan, about 5 inches of snow on the ground up at the northern part
Really?
of Mesa Creek. That's what he said.
There's a lot of snow up there.
There's a snow at your house? So that trench is going to stay open for another week and then you're filling it back in?
I think we're going to try to push this as close as we can towards Thanksgiving to get as much detail as possible. If you spend all that time digging a hole, you want to spend as much time in it as possible, I guess.
Is there a chance you could show some of us that? Putting you on the spot now,
I
but
don't
like,
really know how I would show it to you, but we'll stay tuned. We'll find a way to get pictures to you.
that's a creative no. Nice, Walter. Thank you.
I'm
All
not
right.
going to hold the phone up and be like,
All right. Thank you. Okay, enough of the preliminaries. Let's get to our speaker today. Hannah suggested and has a connection with our speaker, Will Hoover, who's at the University of Washington. And he grew up close to the East Coast in Pennsylvania. His undergraduate days were at Oberlin College in Ohio, and continued to work, oh boy, in West? No, master's?
PhD at Maryland.
PhD at the University of Maryland and has been at the University of Washington a little while. And we're so grateful to have him here talking about episodic tremor and slow slip in a chemically reacting shear zone. Please help me welcome Will.
Thanks, everybody, and thanks for the invite to come talk here. It's been really great to talk with a few of you so far, and hopefully I get to meet more of you after this. Yeah, as Nick said, I'll be talking about chemical reactions in deforming rocks in subduction zones and how that might be related to the production of earthquakes and other seismic phenomena. And this is work that I did, some of it during my PhD at the University of Maryland with Sarah Peniston-Dorland, and some of it during my postdoc at the University of Washington with Kaylee Condit, and then a host of other collaborators who are all really great and from a variety of places. But before I get started, I wanted to just sort of introduce myself and say a little bit more beyond the wonderful introduction I've already gotten from Nick. It's a picture of me when I started my PhD. I'm a petrologist, a structural geologist, and a geochemist. And I'm really interested in the relationships between fluids and deformation, and particularly seismicity. And so this is a complicated question in subduction zones. These are dynamic environments where we have metamorphism, chemical reactions, the movement of fluids, as well as deformation that can produce natural hazards. And so I integrate a lot of different methods. I do geochemistry, looking at tracing the movement of these fluids and the impact they have on rocks and changing the chemistry and the minerals that are in the rocks. I think about how these rocks deform, whether that be looking at the deformation of individual crystals and how those crystals are being distorted, all the way up to the scale of field mapping and looking at, exhumed terrains and their structure. And I also think about the time scales over which these processes are happening, both traditional geochronologic methods where we're looking at time scales of millions of years, as well as using diffusion methods that can get us at now quite short time scales in the rock record down to maybe a few days or weeks. And so I integrate all of this together from the micro scale, looking at inside of individual crystals, all the way to the kilometer scale, looking at big exhumed metamorphic terrains. And I think about these processes from days constrained by diffusion chronometry all the way to millions of years with traditional geochronology. And I take this work that I do in the rock record and I try to connect it to active subduction zones where we're monitoring these processes with geophysical methods. And likewise, try to incorporate results from those geophysical methods in my studies of the rocks. So I take a lot of different methods and approaches to answering this question of how fluids and seismicity might be related to each other. All of the rocks that I'll be talking about today were collected on unceded lands of the Gabrielino Tongva in what's now known as Southern California. And I want to offer a land acknowledgement to affirm their continued sovereignty in the face of settler colonialism and as a commitment to support and advocate for equitable research on their lands. So these sorts of land acknowledgements, I think, are a really important step for us to take as scientists who go and extract often material and certainly information from the landscape where there were original indigenous inhabitants, But the power of these statements, I think, is only to the extent that we go beyond them and take concrete action. And so I just wanted to say a few words about some of the work I've been doing to move beyond land acknowledgements. So I've been doing all of my work on Pimunga, which is now known as Santa Catalina Island. And this is unceded Tongva land. And particularly, I've been working a lot on the mineral talc, which is actually a traditional natural resource of the Tongva. You can see here, let's see, I'll move the cursor over. This is an outcrop of talc on Pimunga, and these sort of knobs that you can see here are partially excavated bowls. So this was an outcrop that was being actively quarried when the Tongva were removed from Catalina Island by Spanish colonizers. And so the rocks that I'm looking at have a lot of cultural and archaeological and spiritual significance to the Tongva. And so I wanted to make sure that I was doing the sampling that I needed to do in as equitable and respectful a way as possible. So this involved consulting with community members about places where I should or should not sample. And I ended up settling on a workflow for sampling where I provided locations I was interested in ahead of time for approval by the tribal members. And as I was doing field work, would take photos and locations of places I wanted to collect a rock, provide them to the tribe for approval to make sure that I wasn't sampling anything that might be archaeologically or culturally significant. Then moving beyond this, I'm also working to return some tangible benefits of this research to the community itself. So organizing community outreach events where I can talk about my research and the sort of deep time history of Pimunga, as well as offering my sort of analytical expertise to help with things like trace element measurements to identify the provenance of archaeological artifacts. And so through this work, I hope not only to be sampling in as respectful a way as possible, but also to make sure that the Tongva community receives some benefit for this work that I've done and material that I've removed from their traditional lands. And you can do this work not just in the places where you do field work. You can do this, at home here in Washington. So there's been work at the University of Washington spearheaded by Nicole Aiken, who's one of Kaylee Condit's graduate students, to do department service to the Duwamish tribe, which is still not federally recognized, but are the traditional inhabitants of the Seattle area. So there's a plot of land in West Seattle that's going to be returned to the tribe, and we've been organizing department work days to do forest restoration work there. There's always, of course, programs like Real Rent Duwamish, where you can make donations to tribal groups to help them regain territory that was taken from them. And so then just a final plug here at the bottom, we have an abstract in AGU. So if any of you are going to AGU, I'd encourage you to go check out Nicole Aiken's abstract about this really great work that she's been doing. So I think now I'll jump into kind of the science. And I wanted to start off by getting everyone here in person and online sort of on the same playing field as far as thinking about what a subduction zone is and what goes on there. So subduction zones are plate boundaries where we have two tectonic plates that are converging, and one that is more dense, oceanic crust, is going to subduct underneath another. And in this case, I'm particularly thinking about an example like the Cascadia subduction zone, where we have subduction beneath a continental plate. So we can think of Seattle being right here. We've got the overriding plate, and we've got this Juan de Fuca oceanic plate that's going underneath. In subduction zones, we have sediments that are deposited on the ocean floor, as well as the oceanic crust and underlying mantle itself that are being returned into the earth. And as this material was transiting at the bottom of the ocean, it takes in a lot of water and it gets relatively cold. And so we can think of subduction zones as being unique, both because we are returning material from the surface into the interior of the earth and because this makes an anomalously cold environment. So we also, of course, above the downgoing plate, we have material as well. This can be sediments in the accretionary prism that have been scraped off and removed from the downgoing plate, as well as continental crust and the underlying mantle. Now, as this plate full of water goes down in the subduction zone, it's going to experience metamorphic reactions where the minerals in the rock are going to change. And minerals that did have a lot of water contained in them might break down to form minerals that have very little water in them. And so Another kind of unique aspect of subduction zones is the production of large volumes of water by these metamorphic reactions. And these fluids are then going to percolate either up dip towards where the plate is entering the subduction zone or vertically into the overlying plate. And this water has been implicated in a lot of the natural hazards that are associated with subduction zones. So subduction zones host explosive volcanoes like Mount St. Helens, as well as large damaging earthquakes. And fluids have been related to all of those processes. Today, I'm going to be specifically speaking about seismic hazards. So in subduction zones, we have megathrust earthquakes. These are the really gigantic earthquakes you're probably familiar with. Things like the 2011 earthquake in Tohoku in Japan and the 2004 Banda Aceh earthquake in Indonesia. But we also get other sorts of seismic phenomena. And today I'll be talking a lot about episodic tremor and slip. So this occurs down dip or sort of further into the subduction zone than where the megathrust earthquakes happen. But we have observed this process preceding some large megathrust earthquakes, and it represents a really important but poorly constrained portion of the overall seismic behavior and seismic cycle in a subduction zone. Episodic tremor and slip is composed of slow slip, which is deformation and movement at of the downgoing slab at a rate that is in between the really rapid motion of an earthquake and the really slow sort of background plate motion of these two plates coming together. And this is accompanied, in the case of episodic tremor and slip, by tectonic tremor, and happens with often a characteristic recurrence interval. So it's happening over and over again in subduction zones. And episodic tremor and slip has been located at the subduction interface. So when we say subduction interface, what we mean is essentially the boundary between the plate that's going down and the plate that is overriding. And this is an area that we can identify geophysically from the surface in subduction zones that are active today. And we can see that it's a fluid-rich area. There's a lot of water moving around at the subduction interface. But beyond that, we can't really resolve the sort of finer scale features and the rock types that are in the subduction interface. And to do this, we need to turn to the rock record. So we can find places where rocks that were buried in subduction zones have been brought back to the surface, and we can look for where the subduction interface is and what it looks like. So what we'll see is that often the subduction interface is characterized by a block and matrix structure. What I mean by this is we have strong blocks of one type of rock that are surrounded by a weak, heavily deformed matrix. And these are often contrasting rock types. And if we have a lot of rocks with different chemistry together and we've got a lot of water in the system, we can also produce a lot of metamorphic and chemical reactions. So I'm showing here actually a picture from Pimunga or Catalina Island. And what we have here is a block that is then surrounded by a really nicely developed reaction zone. So that's a place where the block is reacting with the surrounding matrix because they are different rock types. We have a lot of water moving around here to facilitate those reactions, and it's producing new minerals in this, what we call reaction zone or reaction rind. So this is also a really important process at the subduction interface. And so similarly to how we need to turn to the rock record to see sort of the small scale structure of what the subduction interface looks like, geophysical methods and studies of active subduction zones can tell us a lot about the seismicity that's happening there, its extent, its location, its impact. But if we want to understand the triggers for these processes and the rocks that are hosting the seismicity, to see that kind of fine scale feature, we again need to turn to the rock record. And so today I'll be sort of broadly talking about what rocks can tell us about subduction zone seismicity. I've broken the talk into sort of three different sections. First, I'll be talking about evidence that fluids moving at the subduction interface are moving quite quickly. And I'll follow that by talking about how that fluid movement and the reactions associated with it can produce weak minerals, and then talk about evidence that these weak minerals are hosting, in this case, episodic tremor and slip or slow earthquakes. And so taken all together, I think this is a really nice evidence that we are starting to identify a geologic record of episodic slow earthquakes. And this will, of course, integrate sort of these three different aspects of my work. All of this is going to be work that I'm doing on the Catalina schist on Pimunga or Santa Catalina Island. So this is an exhumed paleosubduction terrain. So all of the rocks on the island that are shown in these kind of brighter colors, used to be buried deep in a subduction zone down to maybe even 50 kilometers depth and have been brought back to the surface. And so we can study them to learn about the processes active during subduction. The Catalina schist has rocks from a lot of different depths and different temperatures. So we can also think of depth and pressure as being sort of interchangeable here. So I've plotted these up here on a diagram of pressure versus temperature. We can see we have rocks from blue schist to amphibolite facies. And many of these rocks are exhumed from the depths where we see episodic tremor and slip today in modern subduction zones. And even better, some of these rocks overlap with the temperature conditions we also expect for those subduction zones. So this is a really great place to go and look for evidence of episodic tremor and slip and subduction zone seismicity in the rock record. So starting off, I want to talk about evidence for rapid fluid movement at the subduction interface, how this might be related to seismicity. So as I said, many of these seismic events in subduction zones are located at the subduction interface, and we know from geophysics that this is a fluid-rich area. But as far as what the relationship is between those two things, we can think of fluids both as a cause of seismicity, where high pore fluid pressures make it easier for earthquakes to nucleate and slip, and in metasomatism. So metasomatism being the chemical changes in the rock sort of catalyzed by fluids, and this can produce weaker minerals that make it easier to produce an earthquake. We can also think of fluid movement as being a consequence of seismicity. So if we're breaking the rock, we can actually create permeability that allows fluids to move through rocks that otherwise would be kind of sealed off, too tightly packed to allow the water to move through it. So these are sort of proposed relationships between subduction zone seismicity and fluids, but this is still very much an open question. And it's only recently where we've been able to start to resolve timescales in the rock record that are sort of starting to move towards what we can observe in active subduction zones today over human lifetimes. So I've plotted here studies constraining the timescales of fluid rock interaction or fluid movement in subduction zones, and they range from timescales on the order of a few weeks all the way to a few hundred years. These are much, much shorter than most geologic processes we think about in the rock record, which are occurring over hundreds of thousands to tens of millions, hundreds of millions, billions of years. And so these really short durations for movement of fluid in subduction zones have been used as an argument for the relationship between seismicity and the movement of fluids. But all of these studies that I've shown here, we're looking at very small scale features within the slab itself and not at the subduction interface. So not actually where the seismicity is occurring. And we might think that the subduction interface might actually have different durations of fluid transport because it's a much larger feature. This can be up to a few kilometers thick and extends for hundreds of kilometers along the top of the downgoing slab. And so it would be really important for making this connection to seismicity to not just know how fast fluid is moving through the slab itself, but how fast it's moving at this interface where the seismicity occurs. And so all of these studies and the work that I'll be talking about in this part of the talk uses a method called lithium diffusion chronometry. So some of you may be familiar with the idea of diffusion, but this is sort of the slow smoothing of initial concentration gradients. And I like to think of this, you can imagine putting a drop of dye in a glass of water, and initially the dye is concentrated right where the drop landed, but over time is going to spread out and eventually end up with the whole glass of water having the same color. So we start out with a gradient, strong gradient in how much dye there is, and eventually it smooths out till it's all uniform. So we can use this idea in thinking about rocks as well, and minerals, where we can use elements moving through the rock or moving through water in the rock to tell us something about and what we know about the characteristic time of that process, to learn something about the duration of events in geologic settings. We like the element lithium because it diffuses really quickly. So it moves really fast through the rock. And this means that it's really sensitive to short events. So even if fluid is just racing through the rock, we're still going to see a record of that in the lithium because it moves so quickly. And so to apply this method, first we want to find a fluid pathway. So in this case, we have a vein here through a high pressure metamorphic rock. And what we can do is measure lithium isotopes starting at that feature and moving away from it into the surrounding rock. And we can see that plotted here on the bottom in the blue diamonds. So we have this measured profile, and we then model diffusion of lithium through the rock. So what I'm showing here is what we would expect the concentration and the isotopic composition of lithium to do through time. So we can take this model and we can stop it when the profile that we see in the model matches the measured data, and then basically read off the time that it took to get to that point. And that tells us a total duration for how long fluid has been moving through that particular feature. So in this case, in this vein, it was 200 years total that they had fluid moving through that vein. And so then we can try to interpret that duration in the context of the rock to learn something about what that might mean. So for this portion of the talk, I'm talking about rocks from the highest grade amphibolite unit in the Catalina schist. These are from depths of modern episodic tremor and slip. And they have a really nice paleo-subduction interface exposure. So one of these sorts of exposures in the rock record, and so we can go there and we can sample material and we can learn something about how quickly fluid is moving at the subduction interface. And in particular, we'll be focusing on the blocks that are within this interface. Again, this is a block and matrix structure, so we have deforming rocks that are moving around these strong, relatively undeformed blocks, and those blocks are what we're going to focus on as sort of a passive recorder of what's going on around them. This is what one of those blocks looks like. We maybe right off the bat can notice that the center of the block where the sunglasses are has a different color than the edge of the block here. What we're seeing here is one of these reaction rinds. So we have the center of the block is maybe what the rock started as, and because of chemical reactions with what's around it, we've produced a new rock type, new minerals at the edge of the block, sort of wrapping it like a blanket. We can zoom into that boundary between the two, and we see that we have, as we would expect, a change in the mineralogy. And this is the result of fluid-mediated chemical reaction. So we're seeing evidence of a chemical reaction here, and a lot of this is going to be accommodated by diffusion. So we might expect to see diffusion across this boundary between different mineralogy and different chemistry. Sure enough, if we measure the lithium isotopes starting on one side of that boundary and moving to the other, we see there's variability, and it's variability that's systematic. So I've sort of put this block rind contact up here for reference. So we can think this is the outside of the block, this is the inside of the block, and we can see that the lithium isotopic composition is changing. So we can apply our diffusion model here and see if we can fit the measured data. That's what I'm plotting here in all of these red lines. This is like 10,000 different results from the model. There are a lot of different parameters that all have uncertainty related to them. And so to make sure we're getting a robust result, we want to incorporate all of that. And I ran this model 1 million times to get 1 million different results and see which ones provided good fits to the data. And so the ones that provided good fits to the data give us a duration of 30 years, minus 31 years, or plus 350 years. So something on the order of a few years to a few hundred years is how long it took for fluid to move through the subduction interface here. And we can see that based on the isotopic patterns, that the fluid is flowing through the rind and through the surrounding matrix, and the block is only interacting by diffusion across this boundary. Now, we did this for 2 different blocks. This may not seem like a lot, but this is the first study to have looked at more than one feature in the same set of rocks. And what we find is they actually have similar durations. Obviously, the error bars are somewhat big on this, but we're getting something on the order of about 45 years for fluid transport in both of these blocks. And these are from different parts of the subduction interface exposure. And so we propose that this represents a regionally pervasive fluid transport that is occurring at the subduction interface. So this is not sort of channelized in one small area of the subduction interface, but rather represents sort of a broad scale movement of water at the subduction interface. As far as how this relates to deformation, we find in the rinds that we have quartz garnet veins. So veins are places where the rock was fractured, water moved through the rock, and it precipitated some minerals, left them behind. So when we find veins, we can see that as direct evidence of fracturing of the rock and fluid flow. And based on the minerals that we find in this vein, we can constrain its timing to be happening at the same time as the fluid movement that we're seeing in our diffusion profile. So not only are we getting a relatively short duration of fluid transport on the order of about 45 years, but we're also seeing brittle fracturing of the rock occurring at the same time. So if we sort of zoom back out from these particular examples and think about what this means, 45 years of fluid transport. That's a lot less than the amount of time it takes us to get these rocks from the surface down to the depth where this is happening. So we're not seeing something that's happening throughout the whole lifetime of these rocks as they're being subducted. This is a very punctuated and short event. The other interesting thing we can notice is that if we plot this up relative to all the other studies that have been done, we see that we don't get an appreciable difference in the duration of fluid transport for this really big subduction interface pathway versus much smaller pathways like small-scale veins or shear zones in the slab itself. So it appears that just because we have a bigger pathway doesn't necessarily mean that it's accommodating a longer duration of fluid transport. And maybe it's the production of these fluids and this water by metamorphic reactions, or maybe the opening of permeability, say by fracturing of the rock, that is controlling how long fluid is moving, not the sort of size of the feature. Now, as I said when I introduced this method, this gives us a total duration of fluid transport through the rock. So total, we had 45 years of fluid transport, but this could be broken down into many, many events. And so if we're thinking about this in the context of this brittle fracturing that's happening and what that might mean for seismicity, we see long-term slow slip events, long-term slow earthquakes that can last up to about 30 years. So in this case, this 45 years of fluid flow could be representing one single event where we break the rock and we create a lot of fracture permeability. Fluid moves through the rock for about 45 years, and this is one single event. We're sort of slowly slipping the whole time. We also see in places like Cascadia, which I've plotted here. So Seattle is up here, we're over here somewhere. So this is a slow slip event that was happening back in 2009 down, I guess that would be on the Oregon coast. And we can see that it goes from slipping to relocked or not slipping over the course of a few weeks. And this is attributed to the precipitation of minerals at the fault surface and driven by the influx of fluids. And so this suggests that perhaps movement of fluid at the subduction interface is actually only happening on the order of days to weeks. And that what we see in this 45-year duration might be many, many, many events that are all being integrated together. It's a little hard to tell right now with the data we have which of those possibilities we're looking at, but we're doing some additional geochemical work looking at within individual minerals to see if we can see many events or a single event recorded. So to wrap up this part of the talk, we see evidence for time-integrated fluid transport durations of about 45 years at the subduction interface. And this is a regionally pervasive fluid transport that's happening near peak metamorphism, so at the depths where we're getting episodic tremor and slip. And we see that this fluid movement is associated with fracturing of the rock. And so we might make some tenuous connections to seismicity. And we can certainly see that there are feedbacks between the movement of fluids, the chemical alteration of the rocks, and deformation. And so I think this is really highlighting how these processes are all interconnected. But if we want to really solidify this connection between fluids and the alteration of rocks and deformation, we need to look at the rocks that are deforming themselves, right? We're looking at this block. It's a passive recorder of the fluid that's coming around it in the surrounding interface matrix. But this rock itself is not deforming. And so it doesn't necessarily tell us about sort of what types of deformation are going on. And it's certainly not necessarily going to record a seismic event itself. And so the deformation is not happening in this block, but it's happening in the material, in this case, that used to be all around it. And so if we want to learn something about deformation, we can turn instead to this weak matrix, right? So we were looking at strong blocks. Now we're looking at weak matrix. So this is where deformation is hosted. We can see in the zoomed in image on the bottom, we have these really beautiful little folds. This is from deforming that material. And this matrix is also impacted equally by the chemical reactions that form the reaction rinds on blocks. So we're also chemically modifying this material. And experimental work and models of deformation at the subduction interface suggest that these chemically reacted rocks are what should be hosting slow earthquakes and episodic tremor and slip. And so this gives us sort of a testable hypothesis we can take to the rock record. We can say, okay, if these are the rocks that should be deforming during a seismic event, let's go and look at them and see if we can find evidence for this. But of course, first we need to make these chemically reacted rocks. So I'm going to talk about how we can form those rocks, where that might be happening, and then that helps us better zoom in on thinking about where this deformation might be hosted. So for this portion of the talk, we're going to move a little bit cooler. We're going to look at some of the lower temperature units, in particularly epidote amphibolite that's highlighted there. This is another unit that's been exhumed from the conditions of modern episodic tremor and slip. And I'll particularly point out that the temperatures that these rocks reached are comparable to what we see in Cascadia, what we see in some of the Japanese subduction zones, say Shikoku, and what we see in Mexico today. So this might be a good analog for the sorts of episodic tremor and slip that's happening, say, beneath Washington. First, we need to find evidence that we're looking at a subduction interface. So if we go to the epidote amphibolite and we produce a geologic map in the field by looking at all of these rocks and sort of tracing their extents. I think my cursor has disappeared, but on the bottom of the map, we can see we've got really nicely layered rocks. This is a coherent ocean plate stratigraphy. This is what we think the downgoing slab looks like. We have ocean crust, and it's overlain by sediments, ocean floor sediments. This makes a lot of sense. We can look at this in a cross-sectional view as well. So on the right-hand side of the cross-section, we can see those same nice layered units. But we also see sitting on top of this one of these block and matrix zones, called a melange zone, where we have blocks of material from the downgoing plate mixed in with this highly deformed and chemically altered matrix. So I think what we're seeing here is a subduction interface that's sitting on top a little bit of the slab that was all removed together and brought back to the surface for us to investigate. And if we want to put this in the context of that subduction zone cross-section again, we can sort of rotate it. And this is sort of what we're looking at here, where we have on the bottom the slab, and then above that the subduction interface. So what does this look like? What does the matrix of that look like? Here's an outcrop of it. It can be kind of hard to work on this rock because it's so weak and easily weathered. But we see that it's composed of layered talc, chlorite, and amphibole-rich rocks. And none of these rock types can be produced by closed system metamorphism of subduction zone inputs. So we can't just take what we started with, metamorphose it, put it under heat and pressure, and get this. We have to have some chemical modification that's going on as well. This requires chemical modification and exchange between the different rock types. So what might these have started as? Based on field relationships, we can say the chlorite-rich rocks are derived from original sedimentary material on the top of the slab. So we see here we have boundary, field relationships where we see these chlorite-rich rocks in contact with metamorphosed sedimentary rocks. And we see that the talc-rich rocks are observed in contact with serpentinite. So this is an ultramafic rock. This is what you might expect if you take the mantle and just add a little water. So what we're seeing here then is that the talc-bearing rocks are formed by modification of mantle rocks. And so we can think of all of this as potentially the juxtaposition of slab sediments with the mantle wedge, which is what we might expect for the depths of episodic tremor and slip in a subduction zone. So if we've sort of put these in order, we have the mantle wedge on top, then we have the talc-bearing rocks, then maybe we have some chlorite-rich rocks, and then we have the slab sediments on the bottom. And this is sort of what we would expect because this is what's below and what's above the subduction interface. This makes a lot of sense. Of course, this has all been mixed up as it's been deformed, but this is probably the sort of starting geometry. So how did we make these rocks? If we know what they probably started as, we can do a quantitative comparison between their original chemistry or their inferred original chemistry and their current chemistry to constrain what was added or removed from them. So we see that the rocks that started as mantle, that have a lot of talc in them, they've lost iron and magnesium, and those same elements have been added to the rocks that started as sediments. So we seem to have exchanged iron and magnesium. Likewise, sodium has gone the other way. We've lost sodium from our sediments and we've added that into our ultramafic rocks. We can also see that there are some elements that are just lost completely from the system. So we've basically flushed all of the potassium out of these rocks by moving fluids through them. And these same fluids are also adding calcium from some external source. So all of these rocks have calcium added to them. So we can't have taken calcium from one and put it in another. So there's some other rock that we're not looking at here that has donated calcium to these rocks. And so sort of what this means conceptually is these rocks were formed by chemical reactions both with each other, so local exchange across these boundaries between different units, as well as losing some material completely and gaining new material from somewhere else. But of course, we want to know where that other material is coming from. Where's that calcium coming from? At these depths, we expect that metabasalts, so the oceanic crust that's been metamorphosed, should be releasing large pulses of fluid because of the breakdown of minerals like lawsonite and chlorite that hold a lot of water in their structure. They break down to form minerals that hold less or no water in their structure, and so that water has to go somewhere and should be released from the rock. Turns out if we just go next door to those slab oceanic crust material that was adjacent to this interface, sure enough, we see veins made of epidote. Epidote is a calcium-rich mineral, and these veins are the direct result of minerals being precipitated from a fluid. So if we have a calcium-rich mineral in a vein, that tells us we must at some point have had a calcium-rich fluid as well. So we see evidence in the field that these rocks are releasing calcium-rich fluids, and these then would be interpreted as going into the subduction interface to add calcium. So thinking about how we make these rocks, I hope I've convinced you that we've identified a subduction interface exposure, and we can look at the matrix rocks and see that they were formed by reaction between slab sediments and the mantle wedge, with a contribution of fluid and calcium from the underlying metabasalt. And based on thermometry and geochronology on these rocks, we can constrain this to all happen at these conditions where we would expect episodic tremor and slip. So we've got the right rocks, we know how they formed, and we know that this happened about where we would expect them to host episodic tremor and slip. So now I'll jump into the last bit of the talk, which is talking about, now that we've formed these weak minerals, how are they deforming, and do we see evidence that they are hosting seismicity? So the subduction interface that we're looking at is dominated by chlorite and talc-rich rocks. These are both minerals that, experimentally speaking, we've shown to be relatively weak. And in particular, talc has the right deformation behavior to be hosting slow slip, slow earthquakes at these conditions. And this is both experimentally and based on models of deformation of the subduction interface. So we want to look at these rocks and see, are they deforming in the right way to confirm or reject this prediction from experiments and models. So rocks that don't have any talc in them, that are dominated by chlorite, we actually see that chlorite is behaving in a sort of unusual way. It's actually quite strong. So on the top here, we have a layer that is made of pure chlorite. It's this sort of gray mineral. And what you can see is it's sort of forming these radial plates, these sort of fan-shaped crystals. And their orientation is all pointing in different directions. And what that means is that we can't easily slide all on the same surface of the crystal all the way across. And instead, we sort of get ourselves in a knot, and that material can't deform at all. So surprisingly, we might expect chlorite to be relatively weak, but instead it seems to be behaving really strong just because of the way that it's oriented. And instead, it's in places where we have relatively small crystals of chlorite that are able to rotate and all align themselves, which you can see in the bottom photo. We have all these sort of plates of chlorite that are aligned. That's where we're able to deform those rocks. And we also are deforming the adjacent actinolite, which is an amphibole mineral. Now, if we turn to the rocks that have talc in them, they behave exactly as we would expect. So we see in the top here, we have all this talc in the pink and the green. We can see all these lines, all these crystal planes are nicely aligned. This is accommodating a lot of deformation. This is exactly what we would expect. But in these rocks, we also see that the actinolite, this amphibole mineral, is being fractured and broken up and ground to pieces. So we've sort of zoomed in a lot here on the bottom, but you can see we have what used to be nice crystal shapes of actinolite that have now been fractured. And on the right-hand side here, we've just got fragments of amphibole left. So this sort of is a conundrum because we have to explain how we're deforming this stronger material, this actinolite, how we're grinding it to pieces when everything around it is really weak. Why is it that the talc is not accommodating all of the deformation and the actinolite is just sort of happily floating along for the ride? And so the best explanation that we can come up with is that we're actually essentially making a giant traffic jam of actinolite. All of these crystals are running into each other, and when you are sort of squishing a bunch of strong stuff into each other, it can make it experience higher stresses than it normally would. And so we're basically making a bunch of giant traffic jams and accidents here, and all of the actinolite is colliding with each other and breaking into pieces. And the most efficient way to do this is if we're moving it really quickly, because all of the talc around it is slipping very, very fast. So we think that this is evidence of rapid deformation of the talc. And we propose that, as predicted by experiments and models, what we're seeing here is slow slip hosted by these talc-rich rocks. And the chlorite-rich rocks are maybe experiencing what we would call background aseismic creep. So just the sort of background plate motion, not any of these sort of sudden seismic events. And this is consistent with the predictions from experiments and models of subduction interface deformation, with one caveat. We have to be able to activate frictional deformation of talc. So this is, we have to be able to slide the talc crystals past each other. And this can be quite hard when you're buried really deep in the earth and everything is getting squished together, right? So it's hard to slide things. You know, if you're trying to slide your hands past each other, if you're pushing them together, it's a lot harder than if you're not. And so we need pore fluid pressure to activate frictional deformation of talc. What is pore fluid pressure? So in a rock, we have little pockets between all of the crystals, and these can be filled with water. And if we increase the pressure of the water in these little spaces, we can actually start to basically pry the mineral crystals apart. And as you do that, it makes it easier and easier for them to slide past each other. And in some cases, we can even push them apart so much that we fracture the rock and we produce a vein. So if this is indeed slow slip, we need to see evidence for high pore fluid pressures, which might be recorded by things such as veins. And sure enough, this is exactly what we see. So here we see a talc-rich rock, and it's got a vein of talc cutting through the bottom of the picture here, and you can see these nice mineral fibers that go across the vein. This is a classic vein texture. And on the bottom here, we can see we have an actinolitite, so an actinolite-rich rock that is cross-cut by quartz veins. So we see field evidence of fluid-driven rock fracture and high pore fluid pressure. So this is great. We have met the minimum requirement of the model and the experiments. Even better, in these veins, what we see are inclusion bands. These end up being crack seal veins. And each of these bands that you can see in this image is formed by one cycle of fracturing of the rock, movement of fluid, and precipitation of minerals. So each of these bands is one event where we broke the rock. And so if you count these up, this is just a portion of one of these veins. We've got tens of cracking events here, and probably in the vein as a whole, we're talking hundreds, maybe even thousands of opening events. And so this is what we would expect if these high pore fluid pressures are producing an episodic process that's happening over and over again, like slow slip. Turns out we need to get these fluids from somewhere. And if we think back to the last section, we had this calcium addition to these rocks from the underlying metabasalts. So this may be, and indeed thermodynamic models predict that this would be the source of these fluids that are driving high pore fluid pressures and producing these veins. We also see that deformation of these rocks is episodic in nature as well, just based on the rock texture. So what we have here is a large crystal of amphibole that originally grew across this boundary between two different layers. Now, to grow a big crystal like this across this boundary, the rock has to be relatively static. It can't be moving a lot. We can't have a lot of deformation. But we now see that this crystal has been broken and rotated. So the rock has now been deformed since that crystal grew. And so what this is evidence of is sort of intermittent static conditions and deformation, which is what we would expect for episodic slow slip, where we have slow slip events happening in the talc-rich rocks and the chlorite-rich rocks deforming during sort of background deformation. So we're moving the deformation back and forth between different rock types based on what the fluid pressure is. And we can see evidence of this in the rock textures. So I think in these subduction interface rocks, we see evidence for rapid deformation of talc that's resulting in the collision and fracturing of actinolite. And we can propose that talc in these rocks is hosting episodic slow slip events. And these are controlled by pore fluid pressure fluctuations that is controlling whether we're seeing slow slip in talc when we have high pore fluid pressures, or when we have low pore fluid pressures, sort of background deformation in all of the rocks around it. And if you want to know more about this, I'm really excited. This work is currently in press in Geophysical Research Letters. So I think with this, I'm gonna wrap up with kind of the overall conclusions and kind of big picture of all of this. So from the first part of the talk, we saw evidence for rapid fluid transport at the subduction interface on the order of maybe a few decades that may represent a single slow slip event or the integration of many, many cycles of episodic tremor and slip. We can see that the matrix around these blocks is formed by both local chemical exchange between different layers and rock types that are at the interface, as well as material that's been added by fluid infiltration. And we think that infiltrating water, the water being added to these rocks and the calcium being added to these rocks is derived from the underlying metabasalt, which thermodynamically has been predicted to break down and release water at these depths. We can see that we have rapid deformation of talc-rich rocks, and we propose that taken all together, this is a geologic record of episodic tremor and slow slip. And more importantly, really highlights that these chemically reacted rocks play a huge role in controlling how subduction zones behave and where we may or may not get seismicity. And so for future work, thinking about subduction zone seismicity and how these rocks deform, we can't simply think about what rocks are being put into the subduction zone, but we also need to think about how these rocks are being chemically modified and what new rocks are being produced. And so this involves not just thinking about deformation, but also thinking about chemistry as well. And so I think with that, I'll take any questions.
Thank you, Will. That was excellent. Do we have questions for Will? We must.
Yeah?
I remember you mentioning the 2011 earthquake. That was like a deep slab one-time event, right? Or is this related to this slow earthquake that you're talking about?
Yeah, so the sort of slow episodic tremor and slip is something that releases a similar, I guess, amount of energy as maybe the smaller end of these big earthquakes, but it happens over such a long period of time that we don't actually feel it. So let's see, if I go back to the example of that Cascadia result that I was showing, let's see, we're getting close. Yeah, so this is a slow slip event that releases the energy of an earthquake, but over a period of weeks. And so we don't get the really sudden movement and then the sort of propagation of that shock wave in the same way. So we see this by GPS stations, but we're not going to feel this. It's in sort of the way that it transfers stress in the subduction zone and the way that, you know, slipping in one place but not in another place might make it more likely that that other place will slip soon. And we've seen sort of evidence of this in these slow slip events happening, say, I think it was before the Chile, most recent big earthquake in Chile. So we think that potentially these slow slip events may be really important for preceding and maybe sort of cascading triggers for bigger earthquakes. So that's sort of the interest in understanding these events particularly. Did that answer your question? I think.
I really appreciated your beyond land acknowledgement statement, and I wonder if you could say a little bit more about that. I'm curious if those conversations with the tribes either changed your sampling strategy, or if you learned something from them that changed your approach or the way you were thinking about it, or if they put the brakes on anything in the process.
Yeah, so I forgot to repeat the last question.
You're fine.
But so the question was, in engaging with the tribal groups around thinking about sampling, how did that sort of change my approach? And I'll say I did my PhD in the Western Alps, and I probably sampled more indiscriminately than I should have. I was going on these big field excursions. I wanted to get everything to make sure I had enough to do a PhD, and so I collected. I've probably looked at 5% of the rocks I collected during that field work. And I think both in talking with the tribal members and sort of hearing their relationship to the land and the importance of sort of not just taking stuff that you might work on sometime down the line just to take it, but really making sure that if you're going to take something from the land, it's something that's really important and that you're going to get something out of. So I certainly have been more judicious in my sampling. And I would say overall, most of the things I ended up sampling were not particularly of significance. The talc areas that were being mined and that had sort of an archaeological aspect to them were really relatively easy to identify and avoid. And a lot of this work, despite being on a beautiful island with a ton of topography and beautiful views, I was mainly working at the bottom of really hot canyons that are sort of often being scoured out. So a lot of the rocks I was looking at were relatively newly exposed. But I will say, this kind of work always comes with the, if you want to do this work, it always comes with the possibility that you're going to get a no when you ask if you can collect these samples. And I think it's really important. And it can be really scary as a researcher, especially an early career researcher. I've written this big postdoc proposal. I'm going to go do the work. And like going out there and finding a rock and then having someone potentially say, no, you can't use that rock is definitely scary. But I think, to do this work right, you have to respect the sovereignty and the respect the relationship that these people have with the land, and that sometimes means not working on something. So that was a great question. Thank you.
Chris, you're on camera. You're on the screen twice. You must have a question. I mean, come on. This is like.
Well, Will, we can talk more about this later, but I was intrigued by your chlorite with the random orientation. And the interpretation that was actually stronger and the deformation was partitioning more where you had that.
Yeah.
Plus chlorite. When I first saw that, I thought, oh, well, that looks like a later formed chlorite vein that might have posted the deformation, but obviously it's not what you were finding. And I was wondering if you could talk a little bit more about that.
Yeah, so we...
Could you repeat that one?
Yeah, sorry. So Chris asked about the sort of layers of chlorite that seem to be behaving relatively strong when we might expect it to be weak, and sort of how those formed and why we think maybe they're not sort of a late process. So a couple of things. It's the same composition of chlorite that we see in the rock around it. And I actually don't think that those are veins. It seems to be places where we've preferentially removed more material from the rock. So that was maybe like, I've used the analogy of like, all of this stuff is a highway for fluids and for chemical change, but maybe there are express lanes where we're getting even more material removed, because we also see the concentration of titanium-rich minerals and of graphite in those layers. And we can actually date the titanium minerals, and they're consistent with sort of prograde to peak metamorphism. So I think we've got a lot of sort of lines of evidence that is sort of a prograde to peak. This is happening sort of at the depths that we think it is when this slow slip is occurring. And then, it seems to be really that it's just how easy is it to rotate those crystals as you deform them. And so in the really big radial ones, we're not deforming them very much, and we're not really able to rotate them because they're so large and sort of puzzle pieced together. And it's only in the really small crystals that are mixed in with a lot of other phases with the amphibole where we're able to rotate them. And as soon as they're all aligned together, then it seems to be behaving as we might expect. So does that answer your question? Yeah, it's a great question. Yeah.
I also have a question about chlorite. So I'm interested again in the directionality of all of that, and I was wondering if you find any significance with that with people, like their use of, like if something has that more messy orientation versus the nicer orientation. Is there something that they preferred, or also did you find more erosion with one or the other, depending on the site that you're working on?
Yeah, that's a great question. So the question was, do we see differences in sort of the surface exposure and the way the rocks are eroding, or in the way that they were used by the Tongva based on sort of the different types of minerals and the structure of the minerals? And I think that's absolutely true. There is a lot of evidence and I think knowledge held by the Tongva that there were different types of these rocks were better for certain uses. So one reason that these talc artifacts were traded all over Southern California and the Southwest is that they could be heated up. And if we think about sort of pre-metal technology, having something that you could put on the fire, heat something up is like not super easy to find. And so there were certain types of talc-rich rock that were used preferentially for sort of cooking implements versus things that maybe weren't put on a fire versus things that were decorative. And I couldn't tell you exactly like which was which. And unfortunately, I haven't been able to like go out with tribal members and look at the rocks themselves. A lot of this was sort of virtual communication of like sending GPS coordinates and photos to them and then getting feedback. But I think certainly there's a lot of knowledge held by the tribal members about sort of what particular rock types were best used for what applications. So yeah, absolutely. That's a great question.
One more, maybe?
Yeah.
You mentioned the article, the boots on the ground one. Just some more information on that.
Yeah, so the question was, I mentioned an article started with boots on the ground. I actually couldn't tell you the title off the top of my head. So this is a lot of the work with the Duwamish in Seattle is work done by Nicole Aiken, who's a graduate student at the University of Washington. She, before grad school, worked in environmental consulting and actually has been sort of leveraging those connections to try to get some free environmental consulting work for the tribe. Because when it comes down to it, like this is sort of post-industrial land that's going to be returned to the tribe, and it could come with a lot of environmental liability. And the sort of people donating the land want to make sure that this is not burdening the tribe with, $1 million lawsuits. So she's been doing really great work with her old company and the tribe and the people who are currently working to restore the land to try to get pro bono work. But this is an abstract at AGU. So if anybody's going to AGU in Chicago, she has this, I think it's like a sort of interactive poster presentation. So there is like a time slot where she's presenting it. But I know, she would love to talk to people about this part of it. I am very much like a cog in the machine that is all of the awesome work Nicole Aiken is doing. So shout out to her for sure.
Thanks for such a great talk, Will. Can we thank him again, please?
Thank you.
If you still want to talk to Will, please come on up. He'll be hanging out here for a little while. If you want to come to lunch with Walter and I and Will and maybe Chris or some combination of that, you are welcome. I don't know if we're going to campus. I didn't even talk to you. You want burgers? Or you want Japanese food or salad
Whatever
or
is
whatever?
fine.
Yeah. So there's opportunities to visit with our guest. He's here even at Cornerstone Pizza, 4:30-ish. You're welcome to join us then as well. So thanks again. Have a good weekend. We'll see you next time.
Thanks, everybody. Do I de-mic now?
You de-mic after you shake my hand because that was just excellent.
Thank you. I'm glad. I hope I towed the line of being approachable to everybody. So,
Totally.
okay,
And that's
awesome.
not easy to do.
Thank you.
I'm just going to turn you off. You can just keep that on. Yeah. So,
Very good, Will.
Thank you.
did you want to join us for lunch or do you want to just do office a little bit later?
Because you were going to bring him by at like
2?
2 or something like that.
Think about it.
Yeah, I know. I'd love to join you guys for lunch. Loads of other stuff.
Okay.
I was glad to hear you.
Yeah. Hannah reserved the table at Cornerstone about 4:30. If you want to join us then,
Yeah.
for sure. I know you mentioned that in the email. Did you want to visit with him before we go to Cornerstone?
Yeah. I
Okay,
think that would be good.
good. So I'll
Maybe you guys can do the lunch.
Good.
You can bring him by my office.
Yes.
Be in there working, and then I can join you guys for dinner.
that sounds great.
Sound good?
Yep.
Sweet.
Okay. Thank you.
So this is a great question, and I think it's really
All right. I think I'm still on the
There is
microphone. Let me
definitely-
get around to.
right there. Like some places where it happens shallowly, but it's really erratic.
Okay.
There are other places where it happens. Yeah. So like the deep episodic tremor and slip happen like every couple of months. You have one of these.
I can't
every
answer any
couple of years you get
questions.
these events. And then
Same thing. I'm
in other
not-
places you
I'm
get
just talking to these guys,
shallow,
Emma.
it'll only be just,
So
like, every once
I
in a
think you can
while,
still hear me, and
things
we've got
relatively
that off.
random.
Yes, as I said
But
before,
also there's sort of a bias
leaving-
by how well we've instrumented these sections. So, like,
leaving
this
some
wasn't even
specific
known until the
comments
early
about
2000s.
Will's talk
And it was
would be
identified here in
helpful. If you're
Cascadia
looking
and
to be able to
Japan.
contribute somehow to this Talk Friday series, that's the thing to do. and maybe not in the live chat, but leaving a YouTube comment down below, maybe when we're done. It would be nice for him to see that positive impact. I thought that was an excellent talk. Hopefully you did too. And as I mentioned before, once we get a bunch of these talks kind of in the can on YouTube recorded, then it's going to be easier for us to get other speakers to come and join us.
And there are definitely differences in sort of
All right.
Patterns,
So
time patterns, spatial
if you
patterns
joined us late,
between different subduction zones that do seem to be real and have something to do with the
we're not doing a talk Friday,
that area, but
next Friday,
it does
November
seem to be
11th.
more
It's a
ubiquitous
federal holiday.
than
but
we may have originally thought.
please come
We originally
back
were like, oh, it's like
and
only
join
ice
us for an
and
Ice Age
maybe
Floods
hot
talk.
subduction zones.
Joel Gombiner
And
is
now we're
excellent.
spread everywhere.
And
Okay,
he's a
maybe
guy that I
there
did
are,
a
like, some
field
aspects
video
of it
with. You
that
might have seen back in May. Joel and I were up talking about his PhD work near Mansfield, Washington. So that's the guy. And he'll be here hopefully in 2 weeks. And then Megan Miller will be talking about her pathway as a woman in science and her intersection with CWU then as well. So let me say goodbye to just a couple of you and then we'll end the stream here. So I was keeping my eye on the live chat during the whole thing. Yes, I was disabling the trolls that we had and hiding them from the channel. So that was me in addition to everything else. So hope that worked. Looks like you enjoyed the talk. To me, that was a perfect combination of detail and also making it understandable for people like me and maybe you as well. Great chat. Hello from Tasmania. Hello from the United States of America. Thank you, everybody. I love you, and we'll see you next time.
Yeah, great question.
Goodbye.
Yeah, thank you
Yeah,
so much.
that's a
for
great
your lecture.
question.
Yeah, no, that was
Yeah.
an amazing lecture. Thank you so
Yeah,
much.
yeah. And are you going to AGU in Chicago? Or?
Sadly, no.
Okay.
No.
Well,
One day.
there may be something available